a grabarlo. Y bueno,
Muy bien.
bienvenidos a todos al seminario Junior. Este es el último seminario de este primer cuatrimestre, que lo cierra VALLE. Está actualmente estudiando el doctorado con Eduardo Villaseñor y Fernando Barbero sobre relatividad general, geometrizada, y bueno, ha estudiado física en el Imperial College y luego el máster de física teórica en el Instituto de Física Teórica. Y bueno, os dejo con ella y seguro que vamos a disfrutar muchísimo de su charla.
Muchas gracias, Carolina. Okay, I'll switch to English now because I promised I will do a seminar in English so that everyone could understand. So it will be more open to everyone at the university to attend as well. Okay, so if you have any questions or anything throughout the seminar, or if you can't hear me, or if you don't understand what I'm saying, please let me know through the chat, and I'll try to solve whatever problems there are with the presentation, okay? So let's just begin. I will be presenting today. What I've tried to do is a very illustrative presentation about how to explain gravity to someone who isn't necessarily a physicist or isn't a professional of the subject. The talk, I've divided it into 3 sections. The first section will try to address the question of what is gravity. Then I've done a sort of strange mathematical interlude. Well, we will try to explain how to measure distances, and this part is necessary for the second part of the talk, where we'll look at black holes and we'll try to talk about what a black hole is. In particular, we will talk about the Schwarzschild solution, which is an approximation of what would happen, for instance, if we would like to measure things around the Earth or around the Sun. And I talk about this in the second part of the talk about black holes because it was I think it was the first time that the discussion of black holes began to take a little bit of like, it was difficult for physicists at the time to understand what was happening at that point, right? So let's get into it. So what is gravity? Before I begin, I would like you, please, if you wouldn't mind, can anyone tell me what gravity is, what they think gravity is? If it's in Spanish, it's fine, I'll translate the definition, but anyone wants to say, what do they think gravity is? I mean, I think we've all learned a little bit what gravity is, like maybe in high school. Okay, so it's an attraction force between masses. That's correct, Jesus. Maybe it is an attraction force between masses, but what is this force? Why is it a force, for instance, that only works downwards and not upwards, like all the forces of gravity? It's a little bit mysterious, right? Anyone else wants to have a shot at saying what gravity is? It's difficult. I'm not. Okay. The curvature of the space. Okay, very good. Okay, we'll get to that point actually. So we'll eventually learn that gravity has something to do with the curvature of the space. So, as I've said, in high school or middle school, I think we've all learned that gravity is a force, as Jesus has said, and it models free fall. Newton's laws tell us that gravity is a force such that that every mass attracts every other mass in the universe, and hence this double-sided arrow that I've put between those apples. Newton assumed that the existence of an attractive force between all massive bodies, and that was a key insight into the nature of what gravity was at the time. He also assumed, for instance, that the existence of an attractive force between all massive bodies didn't require bodily contact. And he'd also assumed that it acted at a distance and instantly. Saying that they're attracted to each other, and in particular to massive objects like the Earth, Newton's laws allowed us to predict the movement of apples falling to the Earth, or also the movement of planets around the Sun, for instance, with Kepler's laws. And it helped a lot to understand the movements of, or the mechanics of the solar system. But this description of Newton is merely an approximation, and it fails when the pole is too strong. So, for instance, here we have Mercury, and it orbits the Sun, but the gravitational pull of the Sun is too strong. And how did they know it was too strong? Because they measured the orbit of Mercury, and what the Newton theory predicted didn't agree with the measured value. It differed by 43 seconds per arc per century. And well, it was just something mysterious at the time. This deviation could not be explained by classical theory of Newton. They tried to consider other theories, like, for instance, the existence of another planet that will be perturbing the orbit of Mercury. And well, they didn't find any evidence for it. And in fact, this object, which they call Volcano, by the way, it doesn't exist. So this mystery, for instance, and other examples of where Newton's theory failed were completely unexplained at the time. It wasn't until 1915 when Einstein proposed a new theory, and this was the general theory of relativity. The general theory of relativity is a very rigorous mathematical model, and it allowed Einstein to describe free fall more accurately. And besides of obviously explaining the Mercury-Perihelion precession that I've just talked about. The key insight was that for Einstein, there is not such a thing that would act at a distance, because it is the fabric of the universe itself which gets distorted and which drags objects into a fall, as Laura has said, like the curvature of space, right? Space-time. In the theory of Einstein, he relates the curvature of the space-time to the distribution of all kinds of energy. But to find this relationship, he needed to find the correct expression between the two, so they will be proportional to each other. Thankfully, previous to Einstein, Riemann, one of the students of Gauss, he had studied how to express the curvature of manifolds, and he had defined what is called the Riemann Sensor, which stores is this object here to the left that stores all the curvature information that that we can have of a space-time. And then he also, Einstein, put all the energy information into what is called formally stress energy momentum tensor. Here I've just put energy information because we can treat tensors for divulgative purposes as just catalogs. And well, he needed to find the relationship between those two. And how to do that, what he did is that he discovered how to extract an appropriate sum of curvature quantities that are within the Riemann curvature tensor that were proportional to these stress energy momentum tensor, or energy information catalog for us here. The thing is that this sum has become so strongly connected to Einstein's theory that it is now named after him. So, I mean, he has the right of naming things after him after all. So the Einstein tensor is what is the combination, the correct combination of curvature terms or curvature quantities that connect curvature to the energy information in space-time. Nevertheless, I mean, if I stop the talk right now and I said, okay, so this is what gravity is, will anyone feel a little bit cheated by what I've just done? Like, do you still feel like you don't have a very intuitive grasp of at what like gravity is? Because probably you do, and I don't blame you. This equation here is the Einstein field equation, is a set of equations that are highly complicated to solve, and they describe how matter moves and how space-time curves. But what is gravity in an intuitive way? So in order to grasp this very complex theory, people throughout time have tried to come up with useful representations to visualize how gravity works. I mentioned it in the abstract of the talk, and the representation that is most often used is that of a large elastic sheet on which massive objects are placed. What do these objects do? Well, they deform the fabric under their weight, and they try to give an image of how does matter curve the fabric of the universe, and also provide an illustration of how massive objects like the Earth here will pull everything in the directions, like marbles in a bowl. So for instance, here what we would expect it to happen is that the apple will fall to the Earth because, well, the Earth is pulling the sheet down and it will fall to the ground. So it tries to answer the question, why does the apple fall, in an intuitive way. At first, this image seems to have a lot of advantages, and it does have advantages because it's very simple and it's intuitive. And it helps us understand something that Newton assumed. And the thing is that bodies attract each other indirectly through an underlying fabric of space-time. So for instance, if we have the Earth and the Sun, then we assume that we have an underlying fabric that is connecting them. So the force of gravity doesn't just act at a distance and instantly. It has something underneath them that that would connect them and therefore sort of explain gravity in its own way. But all this picture of gravity is extremely widespread. It has a number of problems, and apart from that, it's also not very rigorous because it has subtle assumptions that are critically important to understand really what general relativity is and how is it different to other field theories. I'm going to try to solve these misconceptions. I've tried to summarize them into 4 short problems. So let's get to it. So our first problem is that it assumes that objects are placed on space-time like marbles. But in reality, space-time is the fabric of the universe that contains them. Therefore, one improvement that we could do, or we could start with, will be to flatten objects onto the surface to make clearer that they are contained within space-time. Okay, so there's that. Second problem. Second problem is that, as I've said before, as I've said before, it sort of explains gravity by gravity. I mean, to the question, as I said, why does the apple fall on Earth? This visualization seems to answer that it is because the apple is pulled downwards, which causes it to fall like a marble in a bowl. But I mean, it's obvious that it's not acceptable to explain a force that we're trying to model, that is the force of gravity, inside of a space-time using some sort of gravity outside of a space-time, whatever that means. In a curved space-time, objects that follow straight lines may seem to be attracting each other when they are simply following the shortest path possible in a curved spacetime. Like, this is why I put here these 2D ants in the surface of our 2D semisphere. They seem to be attracting to each other, but they're just walking to the North Pole, and they're walking in the straightest line as possible. There's nothing between the ants that is making them getting closer, but they seem to have some sort of force of attraction among them. Therefore, when in free fall, objects move straight ahead. The curvature of space-time gives us the impression that these trajectories are deflected. Okay, so the solution will be that we're not explaining gravity by gravity, but we are explaining it using curved geometry. However, this picture of an elastic sheet is still problematic and is misleading. Actually, we think that if space-time can bend, it is due to existence of higher dimension. This sheet seems to bend into a third dimension, right? It looks like as if it was embedded into another space with a higher dimension. But in reality, this is not the case. And the mathematics of general relativity, what they have about them that is so beautiful is that they don't require any higher spatial dimension for the universe to bend. It is therefore preferable not to represent this sheet as seen from the side, but rather from the top. And what I've done here is use a grid to illustrate the curvature. The lines represent lines of constant curvature, like you would do, for instance, in a contour map. It doesn't mean that if you drop an apple, the lines show you the path of the apple. They just show lines where the curvature is constant. So we've kind of summarized something that is 3D with a curvature component into something that is 2D, and it has a sort of a contour map. Finally, and I think what it is the most important problem with this representation is the fourth problem. That is that our diagram just completely ignores the time dimension. A possibility to improve our diagram will be to, for instance, add small clocks at each point of the grid. In this way, the space grid will become a space-time grid, and we understand that time can flow differently depending on where we are on the grid. Nevertheless, this representation also has a number of problems. It's very hard to ask observers that are at different points of the grid instantly as well what will be the time. And I personally find this representation with the clocks still hard to grasp, because it is still hard to explain or understand what does the apple fall. At least for me, maybe for some of you it's clearer in this way, but I think it's still a little bit confusing. So before solving the fourth problem, let's remember first that space-time is an object. For those of you who maybe know what a manifold is, it is a manifold, but let's just say it is an object with 4 dimensions. It has 3 dimensions of space and 1 dimension of time. In the diagram where we just drawn and we've tried to improve, we have 2 dimensions for all the space. And okay, we have the curvature contour lines for indicating us where does the curvature change, but where is the time? Since there is no time dimension in this diagram, we're not seeing that when a space-time is curved, the time component is also being curved. I mean, space-time is curved, and when the sheet is bending, we should also consider the fact that all dimensions are being bent. So Okay, to really understand this, or to try to understand this, let's go back to the two-dimensional ants, okay? We said that if we are in a curved space, like the surface of a sphere, our 2D ants traveling in straight lines in a sphere to the North Pole will seem to be attracting to each other. Well, they will be getting close to each other, but they're not attracting to each other. Now, because it is impossible to present a four-dimensional picture or geometry in any format, but particularly here in a PDF format, in a PowerPoint presentation, let's imagine that the two dimensions of our 2D sphere are not only spatial, but that we have one that is spatial and one that is a time dimension. What I want you to think about is that time can bend equally as a space. So let's go back to our sheet and let's try to revisit the plastic sheet representation and try to take advantage of its usefulness. Instead of having a sheet that is only space, is only representing space, we will have a sheet that has one dimension of space and another dimension representing time. Imagine that you have an apple and an orange, and a marble, and you drop them across the sheet from one of the sides, okay? They will both be moving forwards across the sheet to the other side. The orange will barely change its trajectory because its mass is bigger than the marble mass. Nevertheless, the marble will move towards the orange because the orange mass is deforming the sheet more than the marble. Therefore, we'll see that both follow straight lines in a curved space, so they are following the shortest path in space, time, and hence they will seem, well, they will be getting closer to each other, but they will seem to be attracting each other, particularly the orange attracting the marble. The same scenario happens when we substitute the orange with the earth and the marble with the apple. In fact, it is the time component of the curvature which explains why does the apple fall when we're considering an apple falling in free fall towards the earth. And with such diagram, we see that both the apple and the earth are always in motion, even when they have no speed at the start of its fall. They're both moving in time. And the same scenario happens to every object in the universe. But for instance, I've put here to the left the diagram of how the Earth orbits the Sun, and this is not obviously how it does it, but it's just a representation. Is following, they're both all the time moving through time, and the Earth is following the shortest path in the gravitational field of the Sun. Is this clear? I think I should probably pause before continuing. Does anyone have any question about this? So the key thing is that the time component is being curved. So objects in free fall move toward each other because the time component of space-time is being curved. Okay, so no questions, I'll just continue. So what is gravity? Einstein's theory of general relativity tells us that the effect we call gravity is different from normal forces. In general relativity, space and time are not necessarily flat, like a piece of paper, but curved when in the presence of matter or energy or momentum or stress, for instance. This curvature is caused by all types of mass and energy, and this gives you a self-consistent and closed and complete set of equations known as the Einstein field equations, which is this equation that we've put at the beginning of it. the masses are just navigating through curved space-time. We cannot see the curvature directly. What we only see is its effects. And those effects are what we call gravity. In the words, for instance, of the very famous John Wheeler, space-time tells matter how to move, and matter tells space-time how to curve. Okay, so how are we doing with time? Okay, so any questions so far? Does anyone kind of maybe has a different view of what gravity is now? Okay, no one says anything, so I hope so. Okay, so visualizations and representations are very useful tools for getting a grasp of the physical world from a simplified perspective, or try to explain it. And what we've done so far is to demystify the concept of gravity, and we've turned it into something that, although may still be abstract, it hopefully makes more sense to you. This first part was very important because before going into the second part, which is going to be a pulse, it is necessary to understand that gravity is a consequence of curvature, not something or a force that just happens to be there and acts at a distance and instantly. But before getting into the second part of the talk, we'll make a brief break. And this brief break is going to be about just how to measure distances in space. I've just called it mathematical interlude because it's very short and just a concept that it will be extremely useful for later on. Okay, so we go back again to kind of high school, and we're going to learn how to measure the distance between 2 points in space. Let's consider, for instance, A and B, and we need to know 2 things to know what is the distance between these 2 points. We need to know in which space we're in. In this case, it's flat 2D space, and we need to choose a coordinate system. Once we've made our choices, in this D, which means the curvature is null, and Cartesian coordinates, for instance, there is an object called a metric which stores all the information to measure distances in a space. So it stores the information about the coordinate choice and the spacetime we're considering. The metric has something inside of it that stores the coordinates, but the coordinates are not something intrinsic of space. They're useful to give name to points and to refer to them to one another. So in this case, for instance, it would be like doing the Pythagoras theorem, sliding or cutting this line between A and B into very small slices, and doing the Pythagorean theorem using this infinitesimal distance. If, for instance, we chose another coordinates, let's say polar coordinates, the metric will change because it will reflect that we've chosen a different sort of coordinates, but we're doing the same space as before. Therefore, the distance between A and B is not affected by the change of coordinates because the space-time underneath is the same. Okay, now the metric we said is stores information about the coordinates and a space. We've changed coordinates and we see that the distance between points doesn't change. What happens if we choose the space-time? So let's consider, for instance, a surface that doesn't have no curvature. So let's consider the surface of the Earth, which can be modeled as a 2D sphere. We do the same. We choose our coordinates, our space, and this fixes the metric, which in turn gives us a way to calculate distance between the points, which is this formula here. Okay, so summary of this very, very short crash course into metric. The metric is an object that stores the information about our choice of coordinates and the space-time we're living in. And with this image in mind, I want you to store this image in mind of what the metric is. Now we're going to continue, and we're going to try to talk about what a black hole is. Okay, so again, it's your turn to tell me. What do you think black hole is, or what is a black hole? Can anyone tell me what is a black hole, or what they've heard, or what they think they are, or something that they know about them? A massive concentration of mass. Okay. Singularity of space-time. Massive star so dense it traps the light in its gravity. Okay. Okay. Very good. Yeah. Okay. So they've gained a lot of reputation in recent years and are one of the hottest topics. High gravity. Yeah. Hottest topics in physics. This year's Nobel Prize has been awarded to 3 scientists who have studied black holes. So they are something that everyone is very puzzled about, and they thinking about black holes a lot. You've all said something. So you've said massive concentration of mass, singularity of the space-time, massive star so dense it traps the light in its gravity, and what I'm gonna try to explain here today, it kind of differs a little bit. So I've in this slide, as you see, I've Googled what is a black hole. So the first result that I got, a little bit, you know, that you can trust the source. I assumed NASA will know what a black hole is. So NASA, for instance, says that a black hole is a place in space. Okay, so a place in space where gravity pulls so much that even light cannot get out. Is everyone content with this definition of a black hole? I mean, I've given you the definition. Now you understand what a black hole is? Because I particularly don't understand what a black hole is if I'm given this information. No, right, Laura? No. I mean, obviously they're kind of right. Okay, it's not like I'm saying NASA is wrong. I'm going to try to explain to you what a black hole is from a very mathematical point of view. Okay, so Jesus asks, if mass creates gravity, how can space create it without mass? If mass creates gravity, how can space create it without mass? So you're asking, how does space create mass, Jesus? Because the news talks about space. Yeah, I mean, maybe that's one of the things that I would correct in this definition of NASA is not a place in space. It's a space or region in space-time rather than in only space, right? And okay, let's just continue. And these questions we continue talking after I've explained a little bit more of the mathematics right behind it. Let's consider first universe, where we have this spherical object. It's a spherical, compact, non-rotating, neutral, astronomical object, okay? In the first part of the talk, I've told you, and we've learned, that energy curves space-time. Therefore, this diagram here, you should tell me, Vaya, this is wrong. I mean, the grid underneath it, if we were be representing lines of constant curvature, it would be wrong because space-time is curved, and you will be correct. In fact, we need to deform this space-time. Now, if I were to ask you, what is the distance between 2 points outside of this object? Well, if we want to know the distance, we need to ask ourselves, what is the metric of this space-time in some coordinates, whatever coordinates, but we need to know what the metric is. This question, well, Carl Schwarzschild in 1916, he he asked himself that question, and he gave a very useful approximation for describing the metric around non-rotating or slowly rotating astronomical objects such as stars or planets. Therefore, this is the metric we can use to measure the distance between 2 points outside of this compact object. And now here comes one of the key points that we have to also learn in this second part of black holes, and it's called the Spartial Radius. The Spartial metric is characterized by this Spartial Radius. I want you to think that, and I want you to consider that every massive object in the universe with spherical symmetry, in principle, has an associated Spartial radius. Okay. Usually, the Spartial radius is less than the real radius of the object, or astronomical object. For instance, the Spartial radius for the Earth is around 9 millimeters, which is really, really small, and for the Sun is around 3 kilometers, which is very small comparing to the Sun's radius. What does this Spartial radius mean physically? The Spartial radius is the size that a body must have in order to have the Newtonian escape velocity equal to the speed of light. Okay, this is a little bit, I'll repeat. Is the size that a body must have in order to have the Newtonian escape velocity, this equation here, equal to the speed of light. Right, so if we say, okay, if the Spartial radius of every object is within that object, then there's no risk of that object being the Spartial radius or smaller. So we will need to, for instance, compress the Earth to less than 9 millimeters to have a region or something that will need an escape velocity of equal or bigger than the speed of light. And the question is this: what if the real radius of an object was, in fact, less than the Spartial radius? I mean, what would happen to the escape velocity of this object? If we substitute a brief substitution here for r, or r less than the Spartial radius, we get here something that is equal or bigger than the speed of light. We're going to go through the Spartial metric step by step into the 4 possibilities that it can offer us, and we're going to discover what happens. So, okay, here we have the Spartial metric inserted into how we will measure infinitesimal distances. We've chosen the coordinates, the Spartial coordinates, and we've chosen the spacetime, which they've just named Schwarzschild. There are separate regions, okay, for this, we're going to call it a function. We can consider when r is bigger than the Spartial radius, so all of this green region we have. In this region, everything is okay, and this is what the region where the metric of the Spartial was intended to be used. The escape velocity of the objects are less than the speed of light, so everything works perfectly. Let's now consider the next scenario and the first interesting region, and this is when r equals the Spartial radius. What we see here is that the second term in the metric is not defined and it blows up. Okay, there might be 2 possibilities. Either we've chosen the coordinates wrong, or in fact there is a true problem with the spacetime at r equals rs, so when we are at the Spartial radius. In this case, and I haven't written it here for simplifying purposes, but it is possible to change coordinates of this metric and to extend the metric, and therefore see that the problem is in fact with the election of coordinates we've done and not with the spacetime itself. So nothing at that point in the fabric of spacetime breaks. Nevertheless, there is something that happens that is still interesting, because And this is because obviously how we have defined, or he defined this Spartial radius, we define it to be the point at which the escape velocity is equal to the speed of light. So it's kind of a circular definition, but what it happens is that at a region, which is, if we ignore this term and we don't consider it, is something that has this this metric, and this metric is the one that needs to be considered for the 2D sphere when I was telling you how to measure distances in the surface of the Earth. So this is the super famous event horizon. Is something that it might be modeled as a 2D sphere that is it has the radius of a Spartial radius of that space-time, and what it sets is horizon, or a limit, is a region from which, if you were in that region, you will need to have the speed of light to escape from it, because the pull of the massive object inside of that Spartial radius will be too strong. So you will need to have at least the speed of light, which takes us to our most important and controversial part, which is the black hole. So R, we've considered R to be bigger than the Spartial radius, R to be the Spartial radius, and now we consider the region from the Spartial radius to inside without the zero. Well, as we've said, the escape velocity of objects before was the speed of light, and if we cross it, then if we just substitute in this formula, we can easily see that we will need to have a speed of light, that we will need to have a velocity, that will be higher than the speed of light. The inverted commas here are to remind ourselves by Einstein that nothing can travel faster than the speed of light. This is the reason why the region inside is called black, because nothing can escape that region once it is within it, not even light. Everything clear now? If anyone has any questions from here, is this like kind of, is this a simplified version of this? In reality, the interior of a black hole, so this blue region, it doesn't use this Spartial metric. It uses the interior Spartial metric, but the properties of it are briefly summarized here. And what I want you to think is that we've crossed a point where the velocity that we will need to have is not possible to achieve. Therefore, this is why all of these information and event horizon paradoxes are formed, because these black holes are regions and objects are amazing places to test our true understanding of physics, because they take it to the limit. Okay, so the last part, is anyone missing anything from this domain or this function? Can anyone tell me what we're missing? I mean, have we considered all points of the space-time? Okay, so if you don't see it, I'll just tell you. We're missing the R equals 0 region, and this is the most disturbing problem, because unfortunately there isn't a problem with the coordinates. There's a problem with the chosen space-time. It doesn't matter how much we change the coordinates or try to extend them, it's just not possible to consider the R equals 0 region. And this is in fact what is called a singularity, because this region is not contemplated within this metric and this space-time. In fact, this singularity is not truly in space-time. So hopefully I've turned this discussion of what a black hole is into what is a singularity. So instead of asking ourselves what is a black hole, maybe next time we should ask ourselves what is a singularity. And well, that's for like a complete other talk. So yeah, thank you for your time, and I hope you have enjoyed it. Maybe we can discuss a little bit more now. If you have any more questions or questions about gravity or black holes, I'm more than happy to continue the discussion here.
Muchísimas gracias, Valle. Hay aquí dos preguntas de Jesús Castro.
Sí, a ver.
La primera es, bueno, puedes leerla, ¿no? If mass creates gravity,
Sí.
how can space...
So Jesus Castro asks, if light manages to escape from a black hole, wouldn't travel slower than c because of the deceleration suffered, I think, as a rocket trying to escape from Earth? I mean, that's not a question we can ask, because light wouldn't be able to escape from a black hole. It's just not possible. We just said, like, let's just go back to the diagram, right? For it to escape from a black hole, from the interior of the black hole, it will need to have a speed faster than the speed of light. So no, I mean, it's just not possible. You are right, sorry, something near as massive as the black hole, I mean. Okay, yeah, Interstellar film, I think it gave a lot of publicity and marketing to black holes. In fact, yeah, they did. In my opinion, I think Interstellar is quite accurate about how gravity and space-time works. So it gives a very good description of how much time bends, and how much it depends on your velocity and how you're moving and where you are within the gravitational field of a massive object, such a massive object as a black hole. So yeah, okay, yeah, I think Interstellar is they had good counsel about physics when they were doing the film. Going back to the Jesus Castro question, light always has the same speed. That's one of the postulates of Einstein's general relativity. The speed of light is constant. It doesn't change. It doesn't matter who is measuring the speed of light. Is the same for all observers. So the speed of light is the same for all observers. So it wouldn't matter. Exactly, yeah. It wouldn't matter who is measuring the speed of light, either if you're closer or farther away from a black hole, the speed of light is always the same. Okay. What about Hawkins radiation? Okay, well, I mean, that's something related to quantum effects. So if you want, I can have another talk talking more about the, for instance, astronomical or astrophysical aspects of black holes, because we haven't discussed here how do black holes form, for instance. So here what we've done is we've talked about the Spartial metric, and we've found region which is called the black hole region, and we found a singularity, a type of singularity in general relativity. But I haven't explained to you how does a black hole form and what happens around a black hole in astronomical terms, because in reality, black holes are not static, most of them. They have charge, they may have different masses, they are absorbing mass around them, so they are moving. They're very dynamical objects. So the Hawking radiation has to do with something a little bit more complicated, but maybe when I've studied a little bit more about general relativity, I can tell you about it, and we can discuss it, because they are very probably you've maybe heard about the information paradox as well. So it has to do with those kind of things, and they're difficult to explain. They're difficult to explain plainly, let's say. If the speed of light does not change, what about Cherenkov radiation? Cherenkov radiation, I don't know what Cherenkov radiation is. Okay, I'm gonna Google it. Just 1 second. Electron radiation emitted from a charged particle versus the electric medium. Okay, yeah, I know what it is. Phase velocity. I don't know. Marcial. Actually, let me check. But I'm pretty sure the speed of light doesn't change. But I'll check. Okay. I don't know the answer to your question. I'll check what the Cherenkov radiation is. Right. Okay. Yeah, the speed of light in vacuum. Sorry. Yeah. Okay. Sorry. Cherenkov radiation is through a dielectric medium. Okay. Yeah. So no, is the maximum. Thank you, Natalia. Yeah. Exactly. Yeah. Thanks. Okay. Laura says, sorry. I didn't. What fixes the Spartial Radius? How much does it change when it absorbs objects that are orbiting around it? The Spartial Radius definition, we had it in this slide. Is defined as this formula, where m is the mass of the space-time that you are considering. So if the Spartial Radius, if the mass that you're considering or you're trying to model, because if you're considering a planet or a star, and you have, for instance, two stars merging, then their mass will increase, and the model, and if you're using the Spartial metric to approximate that scenario, because the Spartial metric is not the exact metric for that scenario, then you would have a Spartial radius bigger. So the bigger the mass, the bigger the Spartial radius. I don't know if that answers your question, Laura. Okay, I'm not sure if there are any more questions. Okay, thank you. I'm glad you liked it. Okay. Thank you all.
Gracias, Valle. Gracias. Bueno, me están felicitando por tu charla por WhatsApp, ¿eh? O sea que les ha encantado.
Well, I mean, if you guys want more things about this topic, I know like black holes and general relativity are very popular nowadays. I can try to prepare another talk maybe for next year, and we can continue this. And I think maybe we missed a little bit more from this talk, like the astronomical point of view. Maybe if I explain how black holes are formed, maybe we can talk about more interesting effects like they've mentioned. So, Jesus Castro, yeah, okay, I can recommend some book about this topic. You mean general relativity or black holes for beginners? Both. I would recommend From A to B by Geroch. So from this guy, from the end, Robert Geroch. It's called, I'll just put here, I think this is the name, From A to B. General Relativity or Special Relativity by Geroch. just search it in Google. I'm not entirely sure that's the exact title, but yeah, it's a really good book. And probably Hawkins has some book as well about black holes. But I can try to check. Oh, okay, Juan, gracias. Yeah. Oh, already read Stephen. Yeah. Let me try to have a look. If you want, give me your email and I can send you an email with some recommendations for each topic.